All right, we are right at the start time, 2 o'clock Eastern Standard Time, so we'll go ahead and get started. First off, good afternoon. I'm Jason Thomas, Technical Project Portfolio Coordinator at America Makes, and your host for today's America Makes TRX webinar series. Just a little background on the TRX webinar series before I introduce our speaker. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium, called the America Makes Technical Review and Webinar Series, was created. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with a broader community. If you or your team are interested in presenting during the TRX webinar series, there will be a link to complete the request form at the end of our series today, or you can contact the America Makes TRX webinar series administrator, Jason Thomas, directly. A few important notes before we kick off the series. At the end of the presentation, there will be an opportunity for a brief question and answer session. If during the presentation you do have a question, please submit it in the Q&A space on your WebEx screen, and I will ask it during the Q&A session. I will do my best to get all the questions answered. Today's webinar is on unfinished business, bringing AM together like never before. Without further ado, it is my pleasure to introduce our speaker, Jason Jones from Hybrid Manufacturing Technologies. Dr. Jason Jones is the pioneer and world's leading authority on hybrid manufacturing, integrating additive manufacturing with mainstream CNC machines. He is the co-founder and CEO of Hybrid Manufacturing Technologies, transforming CNCs and robots into flexible, smart factories with additive, subtractive, and inspection capabilities. Dr. Jones has a PhD in 3D printing from the University of Warwick and has led millions of dollars of AM development and commercialization. He is the author of numerous publications, a distinguished inventor holding dozens of patents. Dr. Jones was a founding member of the ASTM F42 Standards Committee and has steered the development of multiple ASTM, ISO standards and strategies. He has also served as the chair of SMEs, which is the Society of Manufacturing Engineers, Member Council, and AM Community, the largest professional 3D printing community worldwide. Jason, I'll now turn it over to you and your team.
Jason Thomas, thank you so much for the intro, and to America Makes for the invitation to speak here today. To each of you, either good morning, if you're still in the morning, good afternoon, or good evening. I appreciate you joining for the next little while and hope to improve upon your next 35 or 40 minutes, something like that. So let's jump right into it. If you are not familiar with hybrid manufacturing technologies, let me just give you a minute or two of kind of where we're coming from. Firstly, if you're looking on screen and I'm little small speaker in the corner somewhere, if you'll click on speaker view or pin the speaker, hopefully it will go full screen for you. Next, from what we've done in the industry, we pioneered bringing directed energy deposition and then material extrusion into CNC machines. We're the most adopted of the hybrid manufacturing providers. And hopefully that gives you some context for where we're speaking from today. Some of our company values, specifically the middle one, courage, we champion having difficult conversations at hybrid manufacturing. And I hope today not to diminish any of the work that's going on in additive. There's such fantastic work in many areas and many scales, but to ask the questions that will lead us toward a more complete, a more holistic experience, both for newcomers to additive and also for those who have already been using additive effectively for many years. So bearing that in mind, let me give you a little overview of what I think of when I think about bringing additive together. So additive manufacturing or 3D printing does not yet produce highly accurate, super smooth surface finishes when you compare it to something like milling or molding or something like that. As a result, many of the parts require some finishing. Obviously, if they're metal or polymer ceramic, they typically follow a different path. Certainly for metal parts, the majority of them do have some machining or polishing or grinding done on them. So in terms of thinking through what's needed for additive, you've got the finishing elements, and also the inspection requirements get changed up when you do additive. So bearing all of that in mind, a more complex workflow or a typical workflow for maybe a more dense material like a metal often looks like something that's on screen. After you 3D print, you may only be half done with your process, with creating parts. You may have to go for a heat treat, cool down, remove them from the build plate, often a finishing operation, and finally, some type of inspection. This post-processing, as we often refer to it, isn't talked about enough, in my opinion, and often it accounts for somewhere between a quarter and maybe up to half of printed part costs. I've even seen 60% before for safety critical parts that need a lot of attention from inspection. So when we say bring additive together and bring it together like never before, there are a couple of ways to do that, but it's not just additive that we need. We need all of the complementary technologies around additive to really give it its full breadth and get those parts across the finish line. Once you've printed a part, until it's actually finished, it doesn't actually do anybody any good. And so from a identity of hybrid perspective, we refer to products as AMBIT, and we use it as an acronym for integrating technologies. And if you look at the silhouettes in this image on screen from top to bottom, you'll notice silhouettes of what traditionally would be a subtractive CNC, well, even prior to CNC, but milling, turning, drilling, those types of capabilities. The next layer down are silhouettes about additive. And then finally, you've got a triangle and a microscope representing inspection. Each of those three types of processes are represented in the elements of our logo, which when decomposed, literally represent inspection, subtraction, and additive, which are three elements that are critical to getting to finished parts. Often we put those on just about any platform that makes sense, from robots to gantries to milling machines. And bringing additive together with those complementary technologies looks something like this. What you're watching is a milling machine that actually just loaded a metal deposition head. You can see here deposition of a metal matrix composite. This is a tooling insert, and so the edges typically wear the fastest. And we've just reinforced those edges with a different material, a higher performing material. And if you look carefully in the video, you can see that multi-material joint. After deposition, we want to know that what we've deposited is good. And so here we're using an eddy current inspection probe to actually check for surface breaking and shallow subsurface defects in the part. And all of that was done in the same setup. So we migrate from what traditionally might be three different setups and bring them all together so that you can get a fully automated finished product right out of the machine. So in this particular example for this part, again, it's a tooling insert used in making other things. We're looking for a 2 to 3 times service life improvement. Fully burdened cost to add those edges around the edge, if you look behind my hands, was about $13. It adds something like 10 minutes to the cycle time. It's already in a milling machine anyway. We're just using that milling machine in a more flexible approach. And probably most importantly, it provides a no faults forward way to adopt this technology. So you know your parts are good before they leave the machine. We don't know of a more time or cost-effective way of actually producing this particular part. And the same is true of other applications when you look at things starting as, like from a repair perspective. This is a turbocharger from Cummins, a Cummins diesel engine. Likewise, this approach also works on softer materials, polymer composites and those sorts of things. So we literally have taken the approach that in milling, you can change on the fly between different types of cutters. And we've brought that same flexibility to additive and inspection. And in fact, in many cases, those tools load right alongside subtractive heads. So I hope that provides you some background in terms of where we're coming from and why I can describe that additive can be more finished, more polished as it comes out of the machine. So let's level set with kind of some foundational principles that I hope you'll find useful. First, if we look at AM as unfinished business, did I actually just call additive parts unfinished? And I did. And more, obviously there are a few exceptions to everything, but the majority of parts made by additive, if they're going to an end user, typically require some kind of finishing afterwards. We already talked about the fact that the surfaces typically are not as smooth as milling or molding, and the inspection requirements are different, and this part workflow is fairly complicated. In fact, in many cases, this actually is a supply chain issue because maybe not all of these steps are done in-house. So we refer to it as a process chain. It may be done all in-house, or it may be farmed out. You may have heat treatment done somewhere else. You may have finishing done somewhere else. You may have inspection done somewhere else. And when I say there are opportunities to improve that, one of my early insights into this was when we were looking at a remanufacturing application with directed energy deposition. We were able to do the deposition, but then in order to get it finished, it literally traveled. The parts traveled, not just like to a next door building, like in a truck. It was all land-based, but in a truck to another facility. It then, from there, it had to go somewhere else to get inspected. And finally, it came back around. So it was a very long path to getting to finished parts, which clearly, as more and more people adopt additive, it's desirable to compress those, right? To consolidate them, to make it easier. Most people come into additive thinking, oh, I have to master additive, but once they find they've got all this post-processing, it's a lot more than many of them anticipate. So I've thought, how can I summarize today's message in a single symbol? And if I was going to think about a symbol for additive or for additive development, clearly the plus sign is one of those symbols that jumps to mind. So for the rest of today's discussion, I'd like to use this plus symbol as kind of an analogy and a little bit of a map of how additive is developing, both here at Hybrid and within the larger marketplace, so that you can kind of see, as new announcements get made, you have some intuition on how to see where it's going. So as we look at this plus symbol, I'm going to divide it into the vertical stroke, and which represents that process chain, right? It can be supply chain oriented. It's pre and post process. It can, and also, so if we look at this workflow for finishing, it's certainly part of that vertical stroke that represents the process chain required for finished parts. If we look then at the horizontal stroke, I'm going to link that to the materials and the scale, which are addressable by additive and various types of additive. And most of the developments that I see in the marketplace fall along, one of these two directions now that we've kind of mapped it all out. Before I go too far, what I'd love to do is point out a talk given back in January by my colleague Lisa Block. And if you look right down there in the bottom, you can see the title, Breaking Barriers and Ending Segregation in Additive Manufacturing. It was a phenomenal talk. It was actually written to be a twinned talk. So what I am giving is the technical second portion that she already prefaced. So if you want to get the whole story, type into YouTube, Breaking Barriers and Ending Segregation in Additive Manufacturing, which talks a lot about people and our mentalities. And at Hybrid, we do talk about segregation. We talk about segregation of how people think. We talk about segregation of processes that are incompatible, but we also look to overcome many of those. So I highly recommend you look that up on YouTube. Just hearing that and going to see it will be well worth your few minutes you've spent with me so far. So again, this is kind of the technical portion paired with those ideas that Lisa introduced about 5 months ago. So why, where are we at as an industry? Back in 2009, I was one of the founding members of the ASTM F42 committee, which started writing standards. And at that point, we had to decide what to call our industry. Back then, we were definitely, I would say, we're not as far along as I point out in that era. We were definitely well entrenched in prototype making. We were looking toward making final parts. And I describe the early majority now as being in between making prototypes and production parts. Clearly, many people make prototypes. It's a fantastic application for additive. Now, many are also looking toward production parts, and that segment of the market continues to grow in importance and in size as a relative proportion of additive parts. And so if you're not thinking about producing parts in an additive way, we see many people that do low volumes of parts, and especially those that can be customized or tailored, that need light weighting or specific types of composition, now looking to production as additive as a production technique. As we look a little bit further into the distance, we see smart products. And that's now very early adopters are starting to tinker with that. Certainly the research world has been working on that for a decade and a half at least. And it's fun to kind of see this progression from prototypes to production parts all the way to smart products. If we look at the application frequency today in the market, we would put prototypes on the bottom as still the dominant application, with production parts moving up to be close behind it. Smart products are just on the horizon, and we're starting to see some really interesting examples. If we look forward and fast forward a decade, I would argue that the value of many products produced, that this pyramid will actually invert, that prototyping will become so mainstream and so routine that to some degree it will be commoditized. Producing production parts will provide more value, and then the highest value will be smart products that have embedded intelligence and can monitor themselves, etc. So that's kind of a where we are from an applications perspective. Let's look at where we are from a materials perspective. So materials matter an awful lot in additive. You'll recall that on this plus symbol, I'm referring to the horizontal stroke. As additive reaches more and more broadly to more and more materials, the applications that are addressable by it continue to get more and more interesting. So applications development and adoption is usually paced by materials development in additive. So I have up here a little wheel. It's got all different types of materials. You know, clearly there are metals, polymers, ceramics. There are also non-metals and a couple other, you know, materials that don't quite fit that. And sometimes people use energy only to be able to modify those materials or the properties or microstructure as they go. So additive started off heavily entrenched with polymers and you know, maybe some paper and other products that are relatively low density. Then the advent of metal really started taking off in the mid-2000s from being able to access the equipment outside of building it yourselves. And then within 2012, 2013, 2014, metal really entered the scene in a far more prominent way, and we see that continuing now. Certainly Form Next, one of the largest exhibitions worldwide that features metal, 3D printing has grown tremendously, and that will continue. We also see production parts made in ceramics, which is another great process great material going forward. And finally, electronics. We're starting to see the embedding of electronics. And I can see from the Q&A, some people are saying, hey, what do you define by smart products? And what I define by those is having the ability to embed some sort of electronic into the part or product itself. As we move toward trying to print those, we need all of these different material families, from polymers, metals, ceramics, and electronics, to be able to really embed intelligence on the fly as we print. Clearly, pick and place plays an important role there as well. But that's kind of the spectrum of where we're at. We're well centered now on production parts, and more people are adopting it. And just over the horizon, in terms of a mainstream adoption, is smart products. So there are lots of applications. This is just a map of where a lot of those materials fit and how they enable additive. So let's look now. We've done applications and materials. Let's look at the processes, the different additive processes. So here on screen is a very colorful graphic that summarizes all 7 of the standardized families. You could refer now to additive as 7+. There are a few newer techniques that aren't super well categorized within these 7, but this represents the majority of additive processes. We created this as a resource for our employees and now have made it available on the website. Anybody that wants to can go download it. It gives you a little summary of the different categories according to ISO and ASTM and kind of what they're good for. Why are there so many? At one point, I had a very prestigious organization visit. They were getting into additive, and they said to me, and at the time I was a researcher at university, and they said, there are too many types of additive. We're going to come in with our technology, and we're going to really help consolidate. We're going to rationalize away several of the additive techniques. And I thought an awful lot about that and watched as they then launched their system, which is a great system. But from my perspective, it has not rationalized away a bunch of other processes. It just continues to expand. And I think that's because of the very diverse set of applications, and also the fact that each of these 7 families, which is fundamentally represents a set of physics or physics and chemistry together, they're usually really good at either a type of material, maybe things that cross-link, or they may be very good at one type of feedstock, like powder, or pellets, or filament, but not every one of these techniques can accept all the different types of materials that we want, nor can they manage all the different types of feedstock that people would like to use. So as additive has been adopted up to this point, the dominant architecture is a self-contained architecture. It's a box. You walk up to it and it's a box, and then usually a human loads and unloads it. That really is kind of heritage from the early prototyping success that additive experienced and continues to experience. But it works fantastic in a design environment, or a, where you're trying to get prototypes quickly to prove out size and fit and form, and even start to do a little bit of use. But really, that architecture demands that customers make a choice between additive technologies very early on. And from my perspective, I've seen lots of centers of excellence, and when you go to a center of excellence, guess what you see? If they say, hey, we have all the 7 families, you actually see 7 individual machines that each manage one of these sets of physics. While there are many technical reasons that undergird that, from a new user perspective, I would argue that in the future, it would be far easier to accelerate adoption if a single machine were capable of more than one type of additive. In the first 20 years, 2 decades and a little bit of additive, this was prevented by patent protection held by large players that each typically clustered around 1 or 2 of these types of physics, or 7 families. But now we're beyond that time. And I think it's time we revisit it and look at how can we bring these together in a more holistic way. So long as you have additive in a self-contained architecture, there are 2 fundamental limitations. The first of which is that because it's been developed in isolation from mainstream manufacturing, often post-processing, even pre and post-processing, can be more difficult or more cumbersome than it needs to be. The second is I draw this colorful chart as if it's in prison, but not just in prison, but as if each individual technology is in its own individual cell, because they are used almost exclusively in segregation, in a segregated mode. So you only get powder bed fusion, or you only get directed energy deposition, or you only get material extrusion. It's not very often that they intermingle. A little bit in the research world, but in commercial practice, not very much. Referring back to this plus symbol, I link this isolated from mainstream manufacturing with this process chain limitation, which is the vertical stroke on the plus. And then I think about the segregated use of AM, which really segregates material, is segregated by material type and often by scale, feature scale, by that horizontal stroke on the plus side. So looking back again here at this workflow, how can we consolidate it? How can we eliminate the need to move these parts to different places? As it stands now with self-contained architecture, I think a lot of 3D printing, like computing before the internet. There's so much potential and so much power within each individual manufacturing technique, but without intermingling them and network them and harnessing the value they provide, we're not really tapping that full potential. And clearly, borrowing from the consumer electronics world, we have such a beautiful example of harmonizing standards and bringing together physically, electrically, and from a software perspective, many devices now into a hybrid device that does so many of those functions for us. And again, that plus symbol, to me, this represents both the vertical and the horizontal when it comes to both process workflow or process chain and the scale of materials. So as a last foundational piece, I want to talk about the digital step for additive manufacturing. So when I first came into additive, I was learning about the different technologies. It was prior to the standardization movement. And so I was learning all of the individual trademark names and names that companies use without having a full framework or an official set of generic names to apply. And I saw a lot of words that looked like selective laser sintering, which now is often selective laser solidification, also selective laser melting. And I remember having a discussion and with a very bright colleague, David Wimpenny, and I said, why selective? He says, that's the explanation of the digital step. That's why additive doesn't require tooling, because it's a digitally driven process. And what they're conveying in that title of selective is how they're distinguishing between what will be included in a part versus what won't. How do you define the cross section of that part as you build it? So selective, selective, selective. I liked that, and it caught on. Now, as we talk about developments and pushing additive forward, and especially the media often refers to additive as accomplishing X. And collectively, additive does absolutely incredible things. Even in an individual set of physics, each individual family does incredible things. But so often, there's not clarity, there's not transparency for which of the 7 families is being used when somebody says, hey, so-and-so used additive to produce this. So-and-so used additive to produce that. It's just not clear. Likewise, when we look at allocating resource, whether we're a funding body or a research organization or a company, it's sometimes hard to get more granular. And yet, to have really powerful conversations, we have to get granular, right? We have to go to the 7+ individual technologies and discuss their pros and cons at that level to really make a good business case. Now, I'd like to offer, right now it's like all of them together or each of them individually. I'd like to offer some medium ground. And it's this is just a tool for thinking, and possibly a way that either America Makes, our standards bodies, or others could help group these types of additive to make it a little bit simpler, not just for newcomers, but as the commonalities of different tasks are required. So I'd like to use that selective word. And so I've grouped the 7 families by their digital step. And on the left here, I have selective exposure. And selective exposure is selective exposure to energy. You can see that I've listed vat photopolymerization, powder bed fusion, and binder jetting. So selective exposure of a binding agent, an energy, something like that, even chemistry sometimes, to be able to make it work. And here's an example. Here you'll see this is a powder bed fusion machine. It's using an electron beam, but that powder has been globally pre-placed everywhere. And then only the energy is selecting what part of that powder gets consolidated into the part and what doesn't. And at the end of this, you'll watch that powder gets spread across into a new layer. Again, it's a global application of material. And then the selection step is exposure of energy. There you go. Hopefully you saw that spreading going across. So in contrast to that, so selective exposure, these processes tend to shine where you look for geometric freedom. They're really, really good at creating complex internal geometry. In contrast to that is selective deposition. And I'll give you an example here. In this case, rather than having material pre-placed, this material is being placed at the same time it's being consolidated. So this is a laser-based directed energy deposition technique, and it is an example of selective deposition. Included with these, I've listed here 4 of the 7 families, and I include material extrusion, like desktop printers, material jetting, sheet lamination, and directed energy deposition. So roughly the additive families divide half and half between these different types of digital steps. And I'll just add that selective deposition really shines often where you're looking at compositional freedom and the ability to vary what a part is made from, either holistically or even different features or elements or graded compositions are possible with many of those. So this digital step framework, I hope, gives you context. What you'll find often is, especially larger scale additive companies, they will typically cluster around one or the other of these. If you're really interested in this idea of selective exposure versus selective deposition, I wrote a paper a long time ago, about a decade ago actually, and explored that in more depth. So if you're that interested, you can go off and look at it. But I hope as a visualization, this helps you keep separated what's what and what is easier to combine with others. Clearly, as we look at trying to reach across different types of additive, selective deposition is easier. It's a more compatible in nature in terms of creating multiple types of additive together, although powder bed isn't to be excluded, or selective exposure, vats and powder is really how those two break down. Certainly, as you look at critical technology elements, either in your company or within your organizations, I highly advocate that you could actually identify, look, these are needs that apply to all 7 families. These are needs that apply to each, an individual one of the 7 families, but you could also then do it by the digital step. So we've now built a foundation that I hope will help provide clarity to some specific examples now. So looking at this horizontal stroke across this plus sign, which is really aimed at materials and multi-materiality and multiple scales. Clearly, as we look at multiple physics or multiple materials, often we need different types of physics to deposit those different materials. They come in a different feedstock form. They have a different chemistry. They perform, they're handled in a different way and they perform in a different way. And so as we look at these 7 families, the real question is, hey, how can we relook at these 7 families? And what makes sense? How can we break these out of that siloed mentality? So part of our history, as I shared earlier, is that we saw the opportunity to break directed energy deposition out of the silo. And then once we had done that, we actually looked at everything that was a selective deposition process and said these can all very easily be broken out of that self-contained architecture and be commingled, right? They can go together. Once you've got a head or a nozzle, right, that deposits or does what it needs to from a physics perspective, suddenly now those can be co-located together. And you think, okay, well, what does that look like? Well, this is a polymer composites head now being swapped for a metal deposition head. To our knowledge, this is one of the first setups that actually allows deposition of metal and polymer in the same machine. Doesn't use the same head, but it's the same machine. So literally you can swap back and forth on the fly and use metal or polymer together. I'm pleased to share a part from one of our customers. This is from Iowa State University, who are actually using this approach to be able to join metal and composites. And so where you have the capability for multiple materials, not just multiple materials within a narrow family. We've had multi-material where you do different types of acrylics or different fills or that sort of thing. But this is now fundamentally very disparate in nature, combining these different materials. And we know that the various industries, right, from aerospace to automotive, as people look to lightweight, they're struggling with this. How do you join metal and composites and polymers all together? And doing it in a single additive setup really pushes things forward and brings additive together in a way that nobody's probably ever seen, at least not to my knowledge. So it's exciting space, and keep watching that space. You'll see more of it. Also, as we look at additive and we think, okay, how can we expand that horizontal stroke even further to embrace more in an automated mode rather than having to manually move it along? And we look at multiple scales and multiple scales of deposition. Here, I've got several examples. This first example is a fantastic cell, and in this case, they're using multiple types of feedstock, both with a directed energy deposition approach, but we've got wire and powder feedstock represented here, which obviously come in a different scale, but as a feedstock, but also get deposited usually at a different scale. So the wire tends to be geared toward larger parts, and the powder is often used for smaller parts, and particularly where harder materials may be desired that don't draw into wire very easily. Here's another variation. These are deposition heads that we make, and you can see there's different types of different nozzles, and they correspond to different scales and different interactions with the material so that you can optimize what feature you make with each one of those. And here on screen is a video. This is a Mazak hybrid machine that integrates those 3 heads. And there on screen, you saw each of those heads doing their, what they're best at. So you no longer have to have a single head that does everything, or, it's compromised in some areas. You can then optimize on a feature by feature basis what you need. Now, looking here, I'm going to use this idea of how do you branch out with additive and how do you make it more accessible. One of the challenges with additive, one of the blessings and challenges, is that it typically starts with flat layers on a flat build plate. And that's natural when you build parts from scratch. Some types of additive are amenable to adding onto existing parts. And when you do that, frequently then you're getting things that are not planar, not flat, and you have to then decide what to do about them. So in this case, this is a directed energy deposition head. It's onto a flat substrate, no problem, very easily done. right? And there's an example of it in real time. Then you're like, okay, actually I have a tube now and I want to add to the outside surface. You're like, okay, well, I can rotate that tube and then I can address what I need to from the outside. Good job done. And then you get to slightly more difficult scenarios where it's like, actually, I want to add to the inside of this part. Now, bear in mind, this tube is already made. You're not building it layer by layer. Often having a pre-existing tube and adding only high-performance material gives you a very different business case. It enables you to do things often at larger scales and in other areas that are not feasible from an economics perspective for many parts. So you think, okay, well, I could tilt that part on 45 and I could access that with that single nozzle somewhat. And you can, and it is done. But once you're to this place right here, this is actually a compromise. Normally, if you're in directed energy deposition, being normal to the surface is ideal, right? You get to absorb most of the energy, it's the most efficient. Here, you're in a suboptimal condition simply because of the form, right? The access that you want. And so if you're like, hey, I want to clad the inside, as the ideal is to be able to say, actually, I have an angled head, which meets the form factor that I need. So being able to then switch between different heads, as described earlier, often we'll load these into machine tools, which have a tool change arm, and then they can select the right head that's necessary. And so in this case, you can swap from that vertically oriented deposition to an internal cladding head, and you can see that there. So that allows intermingling of different types of features in the same setup. And I'll just show you a quick video so you can see it in context. Most people do quite an elaborate changeover process when they switch from an internal cladding head to an external cladding head. And so the easier we can make this, the easier it is to adopt. So you see here, this is not just internal cladding on a diameter, but you can, well, it is a diameter, but with a spiral path, you can actually then create features and patches and do whatever you want. You can also then switch over to a different type of head, as we just showed, and then deposit up on that upper edge. So now you've got continuous clad on the upper edge and on the inside, and you haven't had to make the whole thing from scratch. So as we look at additive and how we reach out more and more horizontally, we think, okay, multiple types of physics and also multiple implementations to enable scale, right? One of the beauties of additive is that mixture of scale where you got macro scale and finer microstructure, microscale as well. Now, as we head into almost our last little bit, I want to talk about post-processing. Now, that word post-processing represents now the vertical stroke on the plus, right? This is process chain, and it may also extend to supply chain consolidation. I hear a lot in the press about full stack. We are a full stack 3D printing provider. And this term has been borrowed in from the software world, and I accept that, when you do the software for slicing and you engineer some of the material and you do the actual printer, you certainly are embracing larger scope and therefore should have better quality control, et cetera, et cetera. So I'm happy with that at that scale. As we look more broadly with post-processing, very few, if any, 3D printing techniques actually are a full stack process. So in that sense, if we look at post-processing, and in this case, I've taken each of those 7 families and I've said, what if we were going to do, parts that needed additional steps? I realize some of these can be used without all of the steps, but certainly as you look across a post cure in an oven, a stress and heat relief, right? A heat treat to stress relieve things, additional types of curing and finishing and all of those types of steps. Certainly removing support material is a huge one, and removing from a build plate is almost universal. So as we look at all those steps and think of that vertical stroke in the plus sign, how can we consolidate these and make them simpler? Here's a couple of words to think through. They all start with an F. So they're 4 words. Forming is the first, and then fusing. Mainstream 3D printing includes forming and fusing, almost always. Now, they may not be done in the same setup, but if we think about forming, it's shown here with puzzle pieces. We're fundamentally creating a geometry, normally by, in layers, and getting that geometry to as good of a tolerance as the physics will allow. Next, there's a consolidation step. I use fusing here in a very broad sense. Very aware that it could, it may be done with thermal fusion and resolidification, or chemical or solid state means this is a consolidation step generally. 3D printing almost always addresses both of these, not always in the same step. We see a growing number of, I'm going to form the part into a green part, and then it will get sintered downstream, whether it's ceramic or metal or other things. That's an exciting step, an exciting development in our industry, and certainly helps improve many access to those types of materials, but it also creates additional steps. And so once these parts are made, whether they're made in a single setup or more than one, often they need finishing. Certainly, the more dense your material and the more precision you need those surfaces, you have to do more and more energy and effort in the finishing domain. Often this happens with a CNC machine. And then if you look one step beyond that, you need quality assurance. So you need some type of inspection or other means to know this is a good part. And so as we look at forming, fusing, finishing, and finalizing, manufacturing embraces all of those steps, not just the forming and the fusing. So to get to true additive manufacturing, our view at Hybrid is you need to embrace all four of those. And to the degree we can automate and simplify the production process, it becomes easier to adopt and more cost effective. Now, conventional thinking is to say, okay, let's take all of these, F words. That's not, sorry, that wasn't a good summary. All of the words that begin with F, forming, fusing, finishing, and finalizing, and say, well, let's just put a robot between each of them, right? And then we'll eliminate the need for manual handling between each step. And you're like, okay, and there are times where that makes sense, absolutely. If we think about it in more detail, we think about the requirements for finishing, especially for metals and maybe some ceramics and other higher density materials, the question then becomes, is there not a common denominator of a platform that's suitable for all of these and not just some of them? And thereby, can we not unify them so that you end up, with this common denominator platform? In this case, we show a machine tool, which is certainly capable of the motion required to do all of these different steps. And certainly in many cases, we have found that there is a cost advantage in moving to this type of approach where we bring together additive with all of its finishing techniques. So, a couple of examples of this. You already saw one earlier. Did you know that hybrid manufacturing goes on regularly with polymer and polymer composites? And here's a quick view of that. So here you see picking up, this is a polymer extrusion solution, it's pellet fed, printing near net. Right? This is relatively high speed. It's about 2,000 times a desktop printer speed. Now, once that's been deposited, clearly the surfaces are not precision. But in this case, in the same setup, you're able to finish to a very nice surface finish and a high tolerance in terms of part precision, which can then be used as a fixture for either setup or CMM or other types of activities. So this hybrid approach has been seen early on in metals. It's been gaining momentum the last several years. We actually hosted the first event dedicated to polymer hybrid manufacturing back in February and had a phenomenal turnout from 3 continents. And it's really fun to see this philosophy of trying to bring additive together with its complementary technologies all into a single setup. Now, there's a discussion that goes on after additive, and it goes something like this, right? How do you know your part is good inside and out? And often the answer that I get when I walk up and is like, it worked last time. And then the question is everything the same? And if it is, well, great. And if it's not, what if this is the first time you've ever made it? There are so many times we use additive for one-offs or two-offs or very small number of parts. How do you know it's good? So if we review again this post-processing chain, you can see that inspection, how can we get inspection closer to 3D printing so that you don't have sunk costs in heat treat, cool, let's suppose that there was an error during printing. All of this work leading up to that final inspection step would then be wasted effort, which again is a significant, often 25 to 50% of a cost, certainly on metal parts. Can we get something that's rapid and in situ to tell us that the part is good? And there's lots of work on monitoring and instrumenting up 3D printing and additive manufacturing machines, and that is boding very well. Clearly, the customer has to accept these methods. So even as each manufacturer works on in-process monitoring, the jury is still out in many cases how effective it really is. So if we look at what the customer already knows and can accept, and we recently had an opportunity to look at something that was really more of a surface coating type technique. And so we only really needed to inspect about a layer deep. Then the question is, okay, can we look through what possible inspection methods could be done in situ and which ones would be rapid? And you look through and you start to think, okay, really, if you've got a surface coating, you've got dye penetrant, eddy current, and microscopy. Only eddy current is really fast and easily viable in situ, or fairly easily. And so drawing on our experience of producing heads, we then said, okay, let's use the ambit eddy current probe and let's take this through and try to demonstrate what value could be there. So there's the probe right there. And here it is actually being used with a part. Here is a different set of parts. And you can see this has been, dye penetrant is kind of the competing technique. So you see this pink hue on each of these parts. And you look on this right-hand part, you can see some very stark lines. Those are cracks. And the dye penetrant is you spray it on and then you spray a developer on. And when it gets developed, it really shows up very well. So it's a very easy way to spot cracks. And it's fairly convenient, right? It doesn't require a ton of resource. The problem is it takes 15 or 20 minutes for these to become really clear and well developed. And so my team often has to unload those parts. So we said, how can we do it fast enough that we can do it in the machine? And that's what this video shows. So this is real time. This is the eddy current. And here it is inspecting along the inside of a mold. These parts, you can see this red trace going up and down. These were wrong parameters, which caused defects. And then this was the same geometry. And this example shows the correct parameters being used. And you can see that trace now, which is green. So here we have a comparison, wrong parameters, defect count 8, and then right parameters without defects. This represents a level of automation to in-situ inspection that's hard to come by. And here you can see the actual cracks on that part that were detected by the eddy current probe. And there you can see all 8 of those, 100% success rate on that inspection. Even at number 6, that crack is difficult to see without magnification, and yet eddy current is able to easily identify it. Likewise over here, this is a good part with correct parameters. And you can see this green trace, nothing exceeds that defect threshold, which is excellent. So that enables you then to go forward with production of defect-free parts. And that is another example that helps us bring together additive in this framework. So as we round out now, we just will have a quick look at what's the future hold, right? So last time I was asked to speak at America Makes, I presented this very complicated looking graph, but just rest assured, this plus sign is a simplified version of what I tried to express here on the left. The horizontal stroke represents reaching horizontally across multiple types of additive, multiple sets of physics, and also taking those types of physics and applying them at different scales. Then the vertical stroke goes up and down on this chart and represents, once you've added something, if you need to subtract to finish, or do some inspection, or even use energy to modify it, that vertical stroke represents bridging across those. And as we think of that plus sign, you can now visualize the different directions that additive is developing in. As additive gets better and better, we are going to see more and more of this shift from centralized manufacturing to distributed manufacturing, which is clearly a benefit in terms of being close to the user, higher availability, less transport required. It's an exciting era. And also, as we talked earlier, smart products are on the horizon. Here you can see one of our vision slides that shows the embedding of smart, both sensors and also some processing capability inside of a 3D printed structure, leveraging various types of additive. And here is one of our customers, Youngstown State University, that has actually gone to the point of doing that. This is a metal part where they've embedded temperature sensing in process. As we get to that state, we're going to have an infinite amount of data. So we've used the infinity symbol to show that. And clearly we want to leverage that data better and better. So again, rounding out for today, I hope this plus symbol provides you with an imagery and a little mental hook to be able to visualize better and better the different types of additive, the different directions that they are developing. And I'd like to thank you very, very much for joining me today. And I'm happy to take any questions.
All right, thank you, Jason. We'll now head into the Q&A session. Once again, if you have any questions for our and you have not done so already, please go ahead and type it into the question and answer box. I do have a couple of questions here to get started. So I think you answered a couple of these questions that have come in during your talk today, which was great, by the way. So when you showed a visual of all the different machining and the deposition heads, so you do see it being possible in the future to print with different additive materials using that same hybrid machine.
Absolutely. And as I tried to highlight that, selective deposition is an easier first step, although there are certainly hybrid approaches for selective energy exposure as well, as we look at powder bed fusion machines that incorporate milling and other things.
Okay, thank you. And then adding on to that question, when you showed the part with the metal and the composite built onto it, so how is that bond created? Is it a really strong bond, or is that a chemical bond, or is a mechanical bond?
It's a mechanical interlocking bond. So the way in which that metal is shaped allows interlocking. There's negative angle on that. So then it allows the interlocking, and you essentially get to the strength or near the strength of the least strong material, right? So it is quite a strong bond, but bear in mind it's purely mechanical, at least what I've shown here.
Thank you. All right. So you've got another question here. Can you expand upon the difference between production parts and smart products?
So the way we visualize it is that a production part is typically a single material, right? So if it's a ceramic part, it's a pure ceramic part. If it's a metal part, then it's made of metal, or maybe it's got a couple of different metals on it if you've done, some reinforcement with maybe a metal matrix composite, but it's not self-monitoring. It doesn't have enough intelligence in it to actually know and be aware of what's going on around in its environment. As we shift to smart products, and I just touched on it briefly at the end, when you embed a sensor in it and then you can monitor the condition of it, whether it's heat or stress or strain or humidity, other types of things, all of a sudden now that part provides you an automatic way to assess how well it's doing, how far it is through its life cycle, if it needs maintenance, all of those types of things. So a lot of people talk about smart everything, right? And smart really comes in a few different scales, if you will. There's enterprise scale, where every machine in your enterprise could be networked together and you could, know what your uptime is and that sort of thing. Super valuable. What we refer to in terms of smart parts or smart products is actually what you're making with those machines. Can you embed intelligence in them so that in the product's life, you get data out of it, in addition to just knowing about it while it's in, say, a smart machine that's able to produce it? Hope that helps.
Okay, so let's see, got a couple more here. So it starts out with thank you for the presentation. Do you have or plan to develop the capability to connect and automate in-situ sensing, monitoring, and inspection with change of parameters?
So the answer to that is yes, and that's a theme that is being addressed by a number of companies. We see the potential here of producing industrial parts with health monitoring capability, which is really exciting. You have other companies that are now becoming more and more vocal and receiving more and more funding that are really expert in producing, kind of one-off, very complicated or customized electronics in small volumes. And that's also exciting. And those capabilities are in the process of merging. And over the next 5 to 10 years, I think you'll see a lot of that.
All right, let's see, we got another one that came in here. So let's see, let me make sure I get to the beginning of the question. I don't want to cut me off. Okay, so it's equivalent to a step change like the living hinge. Single 1-part based on polypropylene versus 3-part based classical hinge simplifies parts.
I like that as an analogy, and picking up on the living hinge specifically, a decade ago we did some research work with Ducati, the motorcycle company out of Italy, and they wanted customized seats. And the way they build customized seats by hand is they vary the different types of foam that they would include in those seats, right? They'll do a pressure map, and then based on the pressure and how a rider would sit, they would then customize that seat with different materials, right? It's a composition change. When we got into additive back then, we were using a powder bed process and TPU, and we found that it was hard to vary the chemistry on the fly within a powder bed process. So what we did as a consortium, and this involved many people in Europe at the time, was we actually devised structures that were made of the same material but acted like living hinges, and we could then stiffen those or make them less stiff to simulate the difference in composition of foam that had traditionally been done in order to achieve it with a single material. We see a lot of that same philosophy going on now with, modern helmets and other things, prosthetics, a whole bunch of custom parts for people where that's being used. There are some applications, though, where you actually have to have a different composition. And electronics is, clearly there's plastic electronics, but you have to have different behavior. And so the composition has to change. It's not enough just to use a single material for everything and achieve all the electronics or, sensing capabilities that you want.
All right, so I think we have one more here, and if you do have questions, we do have a couple minutes. So if you have a question, please get it in, and I'll make sure to ask it. But let's see, how much can the cost of post-processing steps be reduced by automating them?
We find that frequently, if you took it, and let's just say it's a heavy post-processing thing and you're at 50%, you can often crunch it down to maybe 15%. So from 50 to 15, or if you're at, maybe you're at 30%, you could make it down to 10. So frequently we're eliminating, 50 to 60% of the post-processing burden, sometimes more, sometimes less, but that's just kind of a rough feel. It's obviously part specific.
Okay, nice. All right, so I think I'm gonna ask one more here, and then we'll wrap it up for today. So, how much confidence can a new adopter of AM have with in-situ inspection?
So when we say in-situ inspection, most additive machine manufacturers are developing processes to watch what happens and measure, size, temperature, scale, make sure you're not overfeeding, underfeeding, all that sort of thing. Those activities are really powerful. How well vetted they are is hard to measure, right? Unless you go to that specific manufacturer and ask them for documentation of how they've done it, it's just a little bit hard to measure. One of the approaches that we've taken is to say, let's take industry standard inspection techniques like eddy current, like ultrasound, like laser scanning, so that once it's built, you have comparison back to a log of data that has already been, this process is validated. Yes, it's in a new environment, but you're not trying to recreate every, scrap of data to be able to qualify or vet how well it is. So there's not a good answer across the board. You'll have to look individually at every different type. Over time, we've seen great improvements in our own and in others' technology. So I would encourage you, if you're new, to ask questions and try to find out. And then clearly you're going to be comparing it back. The gold standard is usually CT scanning, which is not cheap, but it is amazing in terms of what it delivers. And typically, if you can reference back to that, then you can have a high degree of confidence that, what you're doing as an interim or a less penetrating type inspection is still valid and helpful.
All right, thank you very much. So that will wrap today's TRX webinar series. I would like to once again thank Jason Jones. That was a great presentation. I really enjoyed it. Thank you. I hope everybody else enjoyed it just as much as I did. If you do have any further questions, please reach out to Hybrid Manufacturing Technologies. And there will be a post-webinar survey going out to all of those who participated. We do really appreciate the time that you take to provide America Makes feedback, so we may continue to improve and strengthen the additive community. And as a reminder, once again, if you think that you or your organization would be interested in sharing on the TRX webinar series, please, you can fill out the form that follows the presentation, or you can reach out to myself, Jason Thomas, at jason.thomas@ncdmm.org. Thank you very much, everyone, for coming and joining us today. Have a great rest of your day.
Thank you, Jason. Thanks all. Appreciate it.
Thanks, Jason. Have a good one.